Okay, morning guys. So, excited for 3 days?
Yeah. What are we doing?
Okay, so here's the plan for this week, just so you guys are aware. I mean, 3-day week, we don't have a lot we're gonna do. Today we're gonna start off. I want to just do some informal review of the first 2 days, and in doing so, I'm going to show you guys some old diploma questions that are on the topics we've learned so far. Then we'll do a new lesson today. And I'm not here tomorrow. I'm at a meeting in Lethbridge for some stuff called something called high school redesign. Anyway, so tomorrow morning, I want you guys to work on one of 3 things. First one would be you can probably start looking at your assignment. By all means, you probably can't do all questions on your assignment. We've done 3 days, but you can probably at least start. We're going to do a lab on Wednesday, so you can probably print that off and at least start looking at some of the post-lab questions. And then, excuse you. What do you say for a hiccup? Same thing as like gesundheit. Anyways. And then I've also got a practice worksheet that you guys can work on as well. So that's basically our plan for the week. Lesson kind of today, tomorrow's kind of a work day, and then Wednesday we'll do a lab. And then, yeah, you get the rest of the week off. Good deal? Okay, let's start with some let's start with what we talked about last week first. Let's just do some informal review. So, historically, scientists, chemists have known about the concept of redox reactions. They just didn't really fully get what they were doing yet. The biggest reason why is that internal models of the atom hadn't really been discovered until like scientists like J.J. Thomson and his cathode ray tubes, Niels Bohr and his understanding of different energy levels. The point I'm trying to make is that scientists didn't even know that electrons, protons, and neutrons existed until, about 150 years ago, give or take. Does that make sense? Maybe 200 years ago. What they did understand, though, was the concept of reducing an ore down to a metal. They could take an ore, like, say, aluminum oxide, Al2O3, and they could turn it into pure aluminum, which is useful. And then they could, say, take things like tin and copper and iron and melt them together if they were pure and form bronze or form, does that make sense? So they understood the concept of reduction, they just didn't know what was happening necessarily on an atomic level. Therefore, reduction became known as taking an ore and turning it to metal. The opposite of reduction was oxidation, where you take a pure metal and basically you rust it. That's why they call it oxidation, because it was being added to oxygen. Now we understand actually that it's not just oxygen that causes oxidation. There's lots of things that can do that. Further to that, we actually know that it's not purely the oxygen that's part of the process. It's actually oxygen and water that typically is involved in the rusting process. I know it's kind of skipping ahead, but let me remind you of this table here. There's a very important, we call it a half reaction, right here, which is, yes, oxygen is involved, but it's actually oxygen being combined with water that actually causes rusting to happen. And I gave the example about how, like, when my wife leaves her bobby pins in my shower, you can totally see how they're kind of rusting on the floor of the shower. Whereas, like my wedding ring, it actually doesn't have the ability to rust because that's actually based on its proximity compared to whether it's above or below on the table. I'll talk about that in a second. Okay, so historically, oxidation add oxygen, reduction turn into a metal. But as scientists kind of learned more and more about what was happening, although they could perform these reactions, they then started to realize that maybe what they more had in common is electrons were changing places. If something gains electrons, we now call that reduction, GER. If something loses electrons, we call it oxidation. Hence the whole Leo the lion says GER concept, which, I don't know, I mean, maybe it's silly, but I mean, I think kids all over the world, at least in English, I guess, are kind of taught that mnemonic to try to remember the concept of losing and getting electrons. Maybe just as importantly as knowing those then words of reduction and oxidation, you have to know what an oxidizing agent and a reducing agent are. Thanks. Oxidizing agents, therefore, are things that cause something else to get oxidized. Therefore, the oxidizing agent is actually what gets reduced. That makes sense? And vice versa. Things that are reducing agents themselves are oxidized. So once you kind of can get that terminology working forward, then we can actually start to talk about the chemistry behind this. So the last thing we talked about on Friday was this idea of a table. And in my mind, one of the analogies I like is like a King of the Ring cage match UFC title fight thing, where this is a ranking as to who the best oxidizing and reducing agents are. Hopefully you've labeled at some point on a data table that these guys are the strongest oxidizing agents. The reason why these guys are the oxidizing agents is because they are being reduced. And I can see that because reduction means the gain of electrons for reduction. And look, this guy right here is gaining electrons. This guy right here is gaining electrons. Sometimes oxidizing and reducing agents, you actually need two of them. Like here, oxygen and water are both the oxidizing agents. Does that make sense? If you like my King of the Ring sort of concept, then really it's a fight for electrons. Whoever is the strongest bully out there manages to steal electrons. So if chlorine is going up in a fight against cadmium, yeah, it has the ability to win. It's strong enough. Whereas the example I gave earlier here, the reason my wedding ring doesn't rust is that gold is actually way up here at the top. In terms of strength, the oxygen-water combination of oxidizing agents is actually not strong enough to steal gold's electrons. And that's probably the biggest reason why gold and silver are so valued. It's not that they're really shiny, because lots of metals are shiny. It's not that they're rare, although they are fairly rare, but it's the fact that their chemical properties allow them to basically not oxidize and basically deteriorate. Does that make sense? So, I mean, compare gold and silver, there it is, with, I mean, what are the other common ones? Copper, tin, nickel, iron. This is actually one of the things we're going to do in our lab on Friday. What I'm going to do is, by the way, the lab we do on Friday is more of a me demonstrating lab again, just based on materials and time constraints of it. I'm going to take a whole bunch of different compounds, and I'm going to basically react them together. And we're going to watch and see whether or not something actually occurs or whether it doesn't. For example, one of the things we'll do on Friday, let's just erase some of this stuff since I'm talking about this. On Friday, I'm going to take some hydrochloric acid. Sorry, Wednesday, because we're not here Friday. On Wednesday, I'm going to take some hydrochloric acid. What's the formula for hydrochloric acid? Okay, HCl. One of the things that hopefully you know about hydrochloric acid, though, is it's a strong acid. And by virtue of it being a strong acid, it should ionize into two different parts. An H plus and a Cl minus. Does that make sense? And long and short of it is that H plus is actually kind of a useful one to work with because it's more or less right in the middle of the table. It's actually been put there on purpose. One day I'll teach you guys what these little numbers right here are, but H plus is basically smack dab in the middle of the table. And what I'm going to do is I'm going to take certain metals and I'm going to put those metals in the hydrochloric acid. And we're going to see which of them actually do something and which of them don't. So as an example, one of the things we'll do is we'll put magnesium metal in hydrochloric acid. And you guys actually did this in a lab earlier this year. Do you guys remember what happens when you put hydrochloric acid and magnesium together? Yeah, they react, it bubbles, and basically the magnesium should completely dissolve. Does that make sense? We'll also take maybe like a strip of iron. Now, iron, although should react with the hydrogen, maybe won't dissolve quite as effectively. Does that make sense? Like you're going to see something, but maybe not quite as much. Then I'm going to take some copper, however, and then put copper in hydrochloric acid. And you should see nothing. Does that make sense? I'm not that brave, but if I wanted to, I guess in theory I should be able to throw my wedding ring in there. And it shouldn't do anything. I'm not going to, but does that make sense? So that's part of what we're going to do on Friday. Is like we're just going to test a whole bunch of reactions and see whether what we expect based on the table actually matches up with what we visually can see. So, does that make sense? Okay, that's basically what we've covered so far. Why don't we try some diploma questions? Because believe it or not, there's actually, with what we've talked about these first 2 days, I can show you examples of questions already. So why don't we try some of these? So here's the first one. 4 reactions. Tell me which one electrons are gained in. Thoughts? Nobody's that brave, eh? Okay, fair enough. Let's talk about charges. What's the charge on this calcium 2+? Well, 2+, right? What's the charge on this Gaussian here? Nothing. Okay. Well, how do you find your way from being positive to being neutral? I mean, in terms of options, I guess what you could do is you could lose some protons. But we know that's not possible, hopefully. Because if you try to lose protons, you change what chemical element it is. So rather than losing protons, maybe what you could do is you could gain some electrons. If this 2 plus here managed to pick up 2 more electrons, then turn it to calcium solid. A was the answer. But let's walk through the other ones just to prove why it's not. Here, you're going from a -1 to a 0. How do you go from -1 to a 0? You'd actually have to lose your electron. Does that make sense? Or you'd have to gain a proton, but again, you can't gain protons. So that one's out. To go from 2 to 3, I guess you'd have to do the same sort of thing. If you're becoming more positive, you either gain more protons or you lose electrons. So that one's out. And this last one here, I find kind of odd. It's actually dissolving. This is actually really going back to something we learned in Chem 20, the idea of taking sodium chloride and turning it into Na plus and Cl minus. This is the dissociation process. What are the charges in NaCl though? Well, the charges were +1 and -1. So did the charges actually change in the last one? And I'd say no, nothing actually changed at all in the last one. Does that make sense? Okay, let's try another one. Which of the following ions could not act as both an oxidizing agent and a reducing agent? Which of the following ions could not act as both oxidizing and reducing agents? It's kind of a loaded question. There's a lot to kind of deconstruct on this one. Okay, so what's an oxidizing agent? Well, an oxidizing agent is something that gets reduced. And hopefully know that reduction is the gain of electrons. So we need to find someone who's capable of gaining electrons. Well, a reducing agent then would get oxidized, which means that he needs to be able to lose electrons. So maybe I'm putting it in like people words now rather than phrasing it the way they did. We need someone who is capable of both gaining and losing electrons. Does that make sense? Alright, so let's talk through these ones here. Let's start at the bottom. Chromium. If chromium wanted to gain electrons, chromium could go from 2 plus down to chromium solid. That's possible. If chromium wanted to lose electrons, chromium can go from 2 plus to 3 plus. Chromium can go to 3 plus, can it? That's an option. Actually, chromium can also go to 7 if you have one of the, or 6 if you have one of the big tables. So this one could go to chromium solid, or it could go to chromium 3 plus, so it can do both. Iron actually has the exact same properties. It could go to iron solid. It could also go to iron 3 plus, so that would work. Tin could go to tin solid. And it can also go to tin 4 plus. But the one that can't go both directions is copper. What are the charges for copper? Yeah, 1 plus and 2 plus. Plus, don't forget, you can actually just have copper as an atom. So that means copper could go to copper 1 plus, or it could go to copper solid. Well, in both of those cases, if it's going from 2 to 1 or from 2 to 0, in both cases it's actually just gaining electrons. But copper doesn't have the ability to lose electrons, because then it would have to go from 2 plus to like a 3 or a 4 or a 5 plus. Does that make sense? Different kind of thinking puzzles, hey? Like it's not a, compared to our first unit, which really involved a solid amount of stoichiometry type math canceling, this one's more of a like problem solving, puzzles. There's one more way you could actually consider this one as well. You have a table in your data booklet that looks like this, that lists all of your oxidizing and reducing agents. I started labeling this table a few minutes ago. These guys are your strongest oxidizing agents. These guys are your strongest reducing agents. What you could do is try to figure out who's on the table where. Oh, by the way, I printed off more overhead transparencies, and I found a way to flip it so that the writing was on the back side. Does anybody want to do one? Anybody else? Oh yeah, for sure.
So you know this construction.
I would suggest try not to use whiteboard markers. I think the whiteboard markers, these ones here, will actually pull off the writing. Although now that it's on the back side, it might work better. But if you can get a hold of like a dry erase one or like a wet erase, that might work. So. Okay, anyways, let's start trying to find some of these species. What was the first one again? It was copper, right? So you just even as an exercise in knowing where things are on the table, try to find copper 2+ on this table somewhere. And then circle it. So here's copper 2+. Can you find copper 2+ on both sides of the table? I'd say, I mean, if you search for a couple of minutes, you'll actually discover, no, that's the only place it is. Whereas some of the other ones that I had listed here were, what else do we got? Tin 2+. I can find you a tin 2+ right here and right there. There, I proved to you that it's both oxidizing and reducing. Chromium 2+ is right here and right here. And what was that last one? Iron, right? Iron 2+, which is found right here and right there. Does that make sense? So 3 of them I can find on both sides of the table, and copper is the one that isn't on both sides. Does that make sense? Let's try another. Okay, silver compounds such as silver nitrate can act as strong oxidizing agents. Quick refresh, if it's an oxidizing agent, it means that it is reduced. And if it's reduced, it means that it, yeah, just based purely on just that information right here. We're looking for someone who's going to gain electrons because it's being reduced. Just purely by the word oxidizing agents. I feel like that even helps narrow it down already. So silver nitrate is a strong oxidizing agent, which means therefore it is reduced, which means that it gains electrons. So hopefully right off the bat you can say, well, it's got to be like not A, because that's wrong. Not oxidized, not oxidized. So if something is reduced, what was the original definition of reduction? To turn into a metal. There. I mean, if you wanted to think of other ways of approaching this, you could say, well, isn't AgNO3 really made up of Ag plus and NO3 minus? I'm going to skip the NO3 minus. What would Ag plus do if it was an oxidizing agent? Well, oxidizing agents gain electrons. Gaining electrons, here, I'll have it gain an electron. And there, I just proved that it turns into silver metal. That's all it said. That is a reduction equation. I could even look back on the table and find that reduction equation right here. Is silver plus a fairly strong oxidizing agent? Yeah, I mean, it's not going to win the UFC title, but it's a solid number 10 world ranking kind of concept. Does that make sense? Like it's fairly high up there. I mean, silver is way better than, you know, copper, tin, iron, or chromium. Make sense? Yeah. Let's try another one. Why don't you guys read it? See whether you can figure it out yourselves. You might be able to see how I've been, in subtle ways, prepping you for questions like this on previous tests, where look at the 4 answers. Like, they're all the same, aren't they? Like, one says gains and gains electrons, one says loses and loses electrons, one undergo, like, you know how like they structure them like that, where there's 2 parts, you kind of flip them around? You can't really BS your way through a question like that. You have to know these words. So, what do you guys think? You have an answer in mind? Which one? D? Yeah, let's talk it through then. Okay, so Fe2 plus is right here. Fe2 plus, I'm not even looking at the answers. It looks like it's going from a 2 plus to a 3 plus. Okay, so it becomes more positive. Okay, well, the only way you can become more positive is to lose electrons. So I'm looking for something that's going to lose electrons. And I know that the acronym for losing electrons is oxidation. So good job if you picked D. What do you guys think? So far, not bad? Okay, here's a different question variety. This is one of my must-knows. Like, I've been doing chem now for, I don't know, 2010 was my first year. There's one of these every test. This is where they're going to give you data, and you need to kind of construct your own partial redox table by kind of working backwards. So I don't think I gave you one quite in this format before. So I'd like to walk you through this one first, and then I've actually got another one just like it on the next slide. Is that okay? So what there is there's a table here where it basically says, let's say that you took X solid and reacted it with Y2 plus. It says there's no reaction there. But X solid does react with Z and W. Well, based on that information, I can start to kind of write a bit of a table, and it would look like this. Z3 plus and W plus, I know have to be above X solid. See how I'm doing that? Because W positive does react with X, and Z3 plus does react with Z. But Y2 plus is going to have to go down here, because Y2 plus does not react with X. That makes sense so far? Let's try the next row. Y solid. So in theory, Y solid should probably be down here. Y solid should probably react with everything. It should react with Z3 plus, which it does. It should react with W plus, which it does. And it should react with X plus, which I hadn't written yet. Right there. Why is there a dash in these columns, by the way? Good, yeah, it doesn't actually react with itself. Okay? Something in the same row as each other on the table, it's not going to react with itself. Because it can't react with its own species. I mean, because what it's doing is it's turning from the solid form into the aqueous form or vice versa. So I've kind of looked at the first two columns now. I think I might have the order figured out, but let's just make sure it's right. Z positive should go right here. Or sorry, Z solid should probably be going right here. Z should not react with X. That's true. Z would not react with X. Z should not react with Y. Yeah, look, Z does not react with Y. But then it says that Z is supposed to react with W. But right here, the way I've written it, that's not right. So what do I need to do? I got to flip these two things around. Does that make sense? So why don't I just cross out W right here. I'll put W plus right here. W solid right there. And now look, Z solid does react with W plus, but Z solid does not react with these guys right here. Make sense? And for the last one, W solid should react with literally nobody. And hopefully that makes sense that W is right up here. It has no ability to react with this one, or that one. So now that I've kind of put together my own little table, the question now is, where's the strongest reducing agent? Where is the strongest reducing agent? Where do we find that on this sort of makeshift table we have? Bottom right. This is the strongest reducing agent, and that's the strongest oxidizing agent. So the strongest reducing agent looks like it's Y solid. Does that make sense? That's a must know. Like, you're going to get one of those questions. I can basically guarantee that. So now that I did one for you, here's a second one. Almost the exact same concept. Only this makes it a little bit trickier. They make it numeric response. See how they've labeled on the chart here from 1 to 4 and 5 to 8? You have to rank the reducing agents, which means that your reducing agents are either going to be ranking the numbers 1 to 4 or ranking the numbers 5 to 8. Does that make sense? You want to try? See what you can do. By the way, this is actually what our lab on Wednesday is going to look like. I'm going to take a whole bunch of chemicals, and basically I'm going to react them with each other. And we're going to do observations, and you guys are going to make a chart that looks something like this. You're going to say, yes, it did something, or no, it didn't do something. And then we're going to try to recreate a table and see whether it fits what the actual table would state. It's like a brain teaser, hey? It's like a chemistry Sudoku. Isn't it? If you're stumped on where to start, sometimes the best thing I find to do is to look for the column where either everybody reacts or nobody reacts. Just because that kind of gives you the top and bottom of the column. That makes sense. So like I might suggest I'm looking at W2 plus. It says that W2 plus reacts with everybody. So that means to me that W2 plus needs to go up here, and that X, Y, and Z are going to have to go down there. Now it might not be in that order, but does that make sense to start? And then I want to figure out who's on the bottom. This column right here says that Y2 plus reacts with nobody. So that means that it looks like Y2 plus should go down here. Because that means that Y2 plus will not react with W, it will not react with X, and it will not react with Z. That makes sense so far? So now I know the top and bottom of the table. The question then is, okay, well, which order do X and Z go in? Makes sense. So then if I look at X, X plus should not react with W, which it wasn't going to. X plus should react with Y, but it's not going to react with Z. So if I write X plus right here, it actually would react with Z spontaneously. So I must have X and Z in the wrong spots. So I'm just going to flip it around and put Z on top of X. So Z needs to go there, X needs to go there. That'll be Z solid, that'll be X solid. Should actually write aqueous there because I've been harping on that for 1.5 years. Okay, let's test the table, see that I did it right. W2 plus should react with everybody, which it did. X plus should react with only Y. Y2 plus should not react with anything. And Z plus should react with both X and Y. So now I have my table put together. Last step, who are the reducing agents? Is it this column or this column that's the reducing agents? Yeah, they're right column. Yeah, these guys are your strongest reducing agents going up. So if I gotta do it in terms of increasing strength, Y is the lowest. So that's 7. X is next, that's 6. Z is 8. And W, wait. Not in terms of increasing strength, I did that backwards. If it asks for it in terms of increasing strength, we have to start with the weakest and work our way up to the strongest. So this one is the strongest. Does that make sense? I was doing it backwards. So this one is the weakest. This one is the strongest. So W is first, then Z, then X, then Y. There's your right answer. Anybody know that one? Let's see. Anybody do what I was originally doing and they have them backwards? Yeah. Read carefully, hey? Okay, does that make sense so far? Does this feel like something that you can work towards? Like, don't get me wrong, I don't expect you to be able to solve this problem after 2 days of electrochem. That's not fair, right? But I mean, through the whole process of, okay, well, we'll try, you know, you'll learn, you'll get better. You know, that's something you can probably at one point be proficient at. Okay, I got 2 more questions, then we'll take a break, then we'll do our notes, okay? So, actually, I think I have 3 more questions. So here's another one just like it. Let's do this one a little bit faster, though. So, rather than making it in a chart format, they're just actually kind of putting it together in like an equation format instead. So, this one of the reasons I picked this though is that they've goofed around a little bit on this one, trying to mess with you. Normally, it's going to go from something positive to something solid. That's normally how the previous ones I've shown you are. Do you see what's the twist on this one though? We've got negatives instead. In what order do I need to write that then to keep the table consistent? It's a reduction table. Does that make sense? A reduction table means we need things to gain electrons. Typically, the way you gain electrons and you get reduced is you go from the positive to a solid. But the way we're going to have to do this one here is we're going to have to take our aqueous ones, like A2 aqueous, and we're going to have to turn it into the A minuses. That's not an Al minus. See how going from a 0 to a negative, that's how you gain electrons? So that's the twist on this particular table is when I start writing it out, like I'll even write the first one out here. A2 apparently seems to react with B negative. So I'm going to write it like this. A2 aqueous should be above B negative aqueous. That makes sense? A2 turns into A negative, and B negative comes from B2. So there's the start of my table. This guy and this guy do react with each other. And then it tells me that C2 does not react with B negative. So here's where B negative is. That means that C2 better be in that location. I'm going to assume that C2 turns into C negative. That works well. And then lastly, it says that D2 reacts with A negative. Well, if here's where A negative is, then for it to react, D2 better be up here. Probably turning into D negative. So this one's just a bit goofy because rather than being a positive turning into a solid as a way of being reduced, here we're gaining electrons by making something that's neutral become negative. So last step then, we need to make sure we do this properly. So we got to go from strongest to weakest. So here's our strongest oxidizing agent. So that's D2, A2, B2, and C2. Sound good? Okay, 2 more questions. Different variety now. Okay, so now I'm changing it up a bit here. Why don't I give you a second to read this one? See if you can figure this one out on your own without me adding too much context. So. Yogurt, bananas, apples, and oranges? We're very serious in here. Very serious. Alright. Where do you look to try to find answers to a question like this? You need that data sheet. And this is actually kind of a lead-in to what we're going to work on today. Let me just grab a copy of a formula sheet to put nearby here. Just take a select this. Copy. Alright, I'm going to start circling some stuff then. Where is Cl minus going to be found? And obviously, you guys are fairly new at the table, so I'll help you out here. Chlorine negative ions are found top right-hand side, right about there. Iodide ions. They're also on the right-hand side, but they're not quite as high up. They're right below hydrogen peroxide. The number next to it, by the way, is 0.54. We'll get to what those numbers mean. Let's do it in steps. Iron 2+. Maybe you remember actually from earlier today, iron 2+ should be on this table a couple different times. You should be able to find an iron 2+. Let's see, right about here at negative 0.54. And you should be able to find an iron 2+ at positive 77. Different sides of the table. Where's nickel? Nickel is on the left-hand side at negative 0.26, I think. Zinc is at negative 0.76. That's in the oxidizing agent side. Calcium and sodium are basically right at the bottom of the table. What? So I've started by just kind of finding all the different ions in the well water. So far, with me? All right, now let's look at the four answers. We want to try to make a pipe to carry water from our home. The question is, what should we make the pipe out of? So I'm going to use a different color now. I'm going to try to identify the 4 different metals here and figure out which one is the best choice for this. So first we need iron solid. Iron solid is going to be right about here. Then I need copper solid. That's going to go right here. Chromium solid is right... Oh, goodness. Oh, chromium is right above iron. And aluminum is right about there. Oh, did I pick the wrong chromium? Where's the chromium I'm looking? Oh, it's this one right here. Thanks, guys. Sorry, my table's pretty small. There. Does that work? Okay, so let's talk through one at a time. Which of these 4 metals would be the best choice? Let's start at the bottom here. Should I use aluminum? Why? Well, aluminum's going to react with many of the ions, right? Aluminum's got the ability to react with zinc, and with iron, and with nickel. That's actually a very poor choice, isn't it? Same thing right here with chromium. Chromium is going to react with the zinc and the iron and the nickel as well. That's a poor choice. What is this one? Iron? Iron's not a bad choice. If it wasn't for the fact that nickel was involved, nickel could cause the iron to basically react. And let's say that iron solid reacted. It would mean that your pipes would corrode. Does that make sense? If the iron solid was to turn into iron 2+, it means the pipes themselves are basically breaking down. They're being oxidized. We don't want that. So the best answer is this copper right here. Because look at how that copper works on the table. The copper is not going to spontaneously react with nickel. This copper right here has no ability to react with iodide, iron, and chlorine up here, because these guys are all in the same column right here. They're all trying to lose electrons. They're all reducing agents. So, copper's your answer. Does that make sense? This sort of concept is what we're going to focus on a bit more today. The idea of using our data booklet to try to interpret a scenario. Let me do one more, and then we'll take a break. All right, so last question here. An aluminum strip gets placed into aqueous copper 2 nitrate. Our question is, figure out the oxidizing agent. So I want to do the exact same thing we just did, actually. Let's take aluminum. If it says an aluminum strip, what does that kind of imply? Solid aluminum, which means it's down there. There's solid aluminum. And it says it gets placed into aqueous. Right off the bat, that actually is going to be something I hope you guys are going to recognize going forward. Aqueous means that it's dissolved in water, which means that we actually need to consider water possibly as a reactant. Now, water's on the table a lot. Okay. I just want to look for the places where water is on the table by itself. And there's two. One of them is up on the top. Where is it here? There it is. Positive 1.23. There's a water sitting way up there. There is also a water sitting down here at negative 83. So, right off the bat, is it possible for aluminum to react with water? Yeah, actually. Yeah, aluminum will rust not just in the presence of oxygen in water, but actually aluminum can rust just if you put it in water by itself. So, that being said, we're not done yet. We also have copper 2 nitrate. Well, copper 2 means we need to look for the Cu2 plus ions. The Cu2 plus ions are way up here, just above the middle of the table at positive 0.34. That's where copper 2 plus is. And then we have to look for nitrate as well, NO3 negative. Nitrate is on this data table a few different times. The most likely culprit you're going to look at is right about here, which is around positive 80. Here's the problem though. This nitrate needs H plus to react. Do we have any reason to believe that H plus exists in the solution though? Not really. It said it was an aqueous solution, so unfortunately that one doesn't work. So what's going to happen then? What reaction is going to take place? Well, think of it now as like a King of the Ring cage match concept. What we've got here is a big fight. You've got copper, water, aluminum, all involved in a royal rumble for electrons. Who's the biggest bully out there? Who is going to steal electrons the best? Coppers. Who's the wimp in the ring? Who's the one who's going to give away their electrons the easiest? Aluminum. Does that make sense? This is the most likely reaction to take place. Now, hypothetically, let's say that the copper ions, they run out for some reason, but they're the limiting reactant. And then the copper is gone, but you still have some aluminum left. Well, then after the copper is gone, water could even still react with aluminum more. But at least at this particular point, this is your strongest oxidizing agent, and this is your strongest reducing agent. So copper 2 plus is your strongest oxidizing agent. Does that make sense? This is the process that I want to walk you through today. The idea of a whole bunch of stuff reacts, and the question is, you predict the reaction, hence the title of today's topic, predicting redox reactions. What we're going to do is we're going to circle a lot of things on our little sheet here, and then we're going to try to figure out, well, who is most likely to react. So find the top one in this column, the bottom one in this column, and that gets you started. Does that make sense? Okay, I've been talking for a while. I hope this was productive. I hope this helped you learn a lot. Take a 5-minute break, and then we'll walk through some notes after this. Okay, why don't we talk through today's notes then? You might have noticed there's only a few slides, and we're really just going to do one example. And I feel like so long as you can kind of get the concept I'm going for here, we can do more examples if you want. Like I passed out a worksheet that has tons of practice questions. But they really always take the same sort of format. Sometimes I like to call this, when you see it on a diploma, I call it a beaker of stuff question. Where basically the concept is you've got a beaker and you combine this and this and this. It's like, I don't know, you're like a chef in the kitchen. A little bit of this, a little bit of that. And then the question is, what's going to happen? And basically the process works the same in all questions. Take one of these sheets here, circle everything, right? Figure out who your strongest oxidizing and strongest reducing agents are, and that'll help you write an equation. So here's some preamble notes though before we get to our example. Redox reactions are all about transferring valence electrons. It's a fight for electrons. It's that Royal Rumble concept of there's a bully out there who's going to try to beat everybody up, and conversely there's someone then who's got to be the weakest. And the person who's the weakest is the one that's going to lose their electrons. So I call it the 5-step method. So, I mean, step 1, basically, list all entities in your data booklet. Basically, just circle it all. Hence the whole, this is why you're using transference concept. I do have a couple of notes here that I need you guys to know about, though, just for help. So, here's the first one. If you have an ionic compound, ionic things should dissociate. So, like we just did this one, if I give you copper nitrate, it means that you can look for copper 2 plus and you can look for NO3 minus. So anything aqueous that's ionic, you can look for each of the individual pieces. Okay. If it's a solution, you have to consider liquid water, because water itself could be part of the reaction. If it ever mentions that it's an acidic solution, you have to look for H+. If it ever mentions that it's a basic solution, you have to look for OH-. Fifth bullet here, there are some oxidizing agents and reducing agents that require more than one thing to make them work. So for example, I already pointed out there's the NO3 minus plus H plus set. If you have NO3 minus, but you don't have H plus, it doesn't work then. You need both. And last bullet, make sure you're careful because there's some things that are actually on both sides of the table. This is one of the reasons why I'm going to give you guys a worksheet, and that worksheet's not for marks, but you really need to do it, mostly to familiarize yourself with this table. Because the more you just practice using the table, the more fluent you're going to be. Does that make sense? So I don't usually give a lot of worksheets that aren't for marks, but you really should do this one just for the practice of just familiarizing yourself. So, second step, after you find your data table, find the strongest and weakest reducing agents, write out the reactions, multiply the half reactions so that the electrons gained equals the electrons lost. When we need to do that, I'll talk about that step. And last step, tell me whether the reaction's spontaneous. You guys can read. Let's hop to the example. So here's my example. This is a beaker of stuff sort of question. We're going to the back of my lab, we're taking some stuff, and we're basically we're mixing it together in the beaker. My question is, we obviously won't do this, by the way. But the question is, like, what's going to happen? So first I'm going to make a list of all the stuff we have. It says it's a solution. Right off the bat, as soon as it means it's a solution, we need to look for water. I'm just going to write out the list first, and I'll circle them a bit. So we need to find liquid water. It says we need potassium permanganate. Okay, well, I know what potassium is. That's a K+ ion. By the way, for a year and a half possibly, I'm harping on you to write down states of matter for this moment. Because there's a huge difference between potassium aqueous positive and potassium solid. Does that make sense? So that's going to be the potassium aqueous. You also need permanganate. Anybody know what permanganate is? Where do you find it? Yeah, it's one of those polyatomics that on the data booklet they'd hide up on the chart up here. MnO4 1 minus, right? Okay. Okay, then it says an acidic solution. Well, we've already accounted for the solution part by adding water already, but if it's going to be acidic, we need to account for H+ ions as well. Because anything acidic is going to ionize into hydrogens. We also have iron 2 sulfate. So iron 2 means we need the iron 2+ ions. And sulfate is SO4 minus. 2 minus, actually. Again, aqueous. States of matter. Matter. Okay, next step. Now that I know what I'm looking for in my beaker of stuff, let's find it all. Again, that's probably the whole reason why I want you to do this worksheet, so that you get familiar with this table. Because there's nothing worse than wasting 5 minutes searching around on the table going, I can't find where cadmium is. Right? Like that's so frustrating. You can't waste your time on that. So, what do I got listed first? I guess here I've got H+ listed first. Now, H+ is on the table by itself in one location. It's by itself right here. Right in the middle at 0, 0, 0. Again, we'll talk about the numbers at a different point in the course. Hydrogen is listed on the table in a lot of other locations, but unless both are present, it's no good to us. So, then I need to look for water. Water is also on the table in many locations, but by itself, it's located way up here at the top at 123 as a reducing agent. And it's also found more or less at the bottom at -83 as an oxidizing agent. Those are the main places I found water. Iron 2 plus is actually also on the table in more than one location. Let's see. Iron 2 plus is going to be found on the right-hand side at 77, and on the left-hand side at negative 0.45. Potassium positive is found way at the bottom, basically as low on the bottom as you can be, negative 293. SO4 2 negative. It's also one that's found in more than one location. SO4 2 negative is found at positive 17, right about here. However, SO4 2 negative only works on that reaction if you have H plus, which we have. Sounds good. There's some other SO4s on this table as well. There's one way up here. There's an SO4 2 negative right up here. But it needs lead 4 oxide to work, so that's out. I think that's more or less it that's useful. Oh no, there's one down here. There's an SO4 2 negative and water reaction at negative 93 that we could consider. Lastly, we need to look for MnO4 minus. And MnO4 minus is actually the third one from the top, way up here. But again, in order to use the MnO4 minus, you would need to have H plus ions, which we do. Okay. Wow, that's a lot, eh? You can see why I like to call it the beaker of stuff. There's a lot of possible reactions that could take place. And I could write probably, well, actually, for those of you guys in my math class, this is a terms and question. There's a 1, 2, 3, 4, 5, 6, 7 times 2. There's 14 reactions I can react. Not all of them are spontaneous, though. So I need to find the spontaneous reaction that's going to occur. This is the strongest oxidizing agent. That is the strongest reducing agent that I have. Does that make sense? So all of that work was really to do this. I need to now write out the two equations. So I'm going to write them up here. I'm just going to erase this so that I have it off to the side here. First equation is MnO4 minus and 8 hydrogens and 5 electrons. By the way, the electron number, very important. We're going to do that in the next step here, but we need to know the right number of electrons. And it's going to turn into, I'm really running out of room here, I apologize, Mn2 plus aqueous and 4 waters. So far, so good. Is that a reduction or an oxidation reaction? What'd you say? It is reduction, yeah. Anything that's written in the forward direction is gaining electrons and therefore reducing. Which means that for the other species, which is the iron 2 plus, the iron 2 plus is actually going to go back the other way. So I actually need to flip the other reaction. Similar to in the first unit, there was the decomposition and formation. We have a table that's written about formation, but we can use it for decomposition. Same thing here. Although the table is written as a reduction table, I can make it oxidation by taking that Fe2 plus and making it go backwards into 1 electron plus Fe2 plus. Does that make sense? Using Hess's law, I can start to kind of fit this thing together, but it's not quite ready to be fit together based on electrons. This guy is going to require 5 electrons. This one here only emits 1. Yeah, times it by 5. So, basically just times this reaction by 5, times that by 5, times that by 5. Because what should now be able to happen is the 5 electrons that the permanganate requires should be matched by the 5 electrons that iron emits. Now I should be able to write an entire equation. Thanks, Brad. What we're going to have then is an MnO4 minus, that's aqueous, 8 hydrogens, which are also aqueous, and 5 Fe2 pluses, again, also aqueous. And those, sorry, this is like the worst way of writing this. Those are going to turn into Mn2 plus aqueuses, 4 water liquids, and 5 iron 2 pluses. You looking for something?
Just
Me?
math 31s.
Oh. Actually, just
Do you guys have a quiz this afternoon? It's printed. It's at Shirley's desk. I don't know if you guys have to, but she will put it on there.
All right. So this right here, I know I kind of wrote it half sideways, but there's our equation. Okay. We should double check a couple of things just to make sure that it's been done properly. We should make sure it's balanced. It should be, by the way. If you did it properly, it should be balanced, but let's double check. Here is 1 Mn, manganese, and right here is 1 manganese. Now, I know one of them has a charge, but we'll get to that later, but in terms of atoms, that's equal. Here's 4 oxygens, 8 hydrogens. Well, 4 times 2 is 8 hydrogens. And 5 iron to 5 iron. But more importantly, we also need to make sure that the charges are balanced. Okay. To begin with, we have a net charge of a -1, then 8 positive more, and then 10 positive more right there. So we have a grand total of 17 positives on the one side to begin with. Well, if you look at this second half over here, this is supposed to be a 3 plus. Ooh. Someone pointed that out. You guys ready this 3 plus, or did you just write whatever I wrote? Okay, good. Because that charge makes a huge difference. Here's why. If I had not written a 3 plus right there, 5 times 3 is 15, and then these 2 more would have given me 17. But if this had only been 5 times 2, that would have only been 10, plus 2 more, which is not 17. So now there's plus 17 to start and finish. So not only have we combined these 2 half reactions, proven that the chemical species are balanced, but we've actually proven that charges are balanced as well. Last question. Is this equation that I wrote on paper, will it occur? Just because I wrote it on paper doesn't mean it actually will occur. Is it spontaneous? It is. How do we know that? Well, based on this data table, it has the right, I don't know, trajectory with each other. So sometimes you might see then either an S or an NS written over top of the arrow, just to indicate spontaneity. Remember, spontaneous in chemistry does not mean that it happens quickly. It just means that it happens. It's an odd word choice, isn't it, compared to what you're used to for spontaneous? Spontaneous just means that it will occur. Does that make sense? Cool. Okay. Rinse, lather, repeat, basically. That's the same sort of process. I don't really feel the need to walk you through like 1,000 more examples. I do have one more thing to talk about, though. A really important term that's going to probably be on your diploma. It's just another definition. You just need to know what it occurs. It's called disproportionation, or less likely, they might either call it auto-oxidation or self-oxidation. Okay. All of those mean the same thing. It basically refers to a scenario where a chemical compound, the same thing, has the ability to both oxidate and reduce simultaneously. This is a pretty rare thing to happen. In fact, it actually probably will not happen naturally. We'll eventually get to the concept of batteries. I don't want to jump too far ahead yet, but I guess a bit of a spoiler alert. If you're wondering what all of these numbers on the side right here refer to, it refers to how many volts a battery would be able to produce based on using those chemicals. Does that make sense? But let's get to that at the right time. So, auto-oxidation would be where you have like the same thing in an equation, both oxidizing and reducing at the same time. Here's an example of an equation where this would occur. Let's say you started with Fe2+. Fe2+ has the ability to add electrons and become Fe solid. Or Fe2+ has the ability to turn into Fe3+ and lose an electron. In this particular example here, according to Hess's law, these electrons here would have canceled. But these Fe2 pluses, they'd actually combine. This species right here would be considered auto-oxidizing, or you could say that it's disproportionation, because the Fe2 plus is both going down to a 0 charge and going up to a +3 charge. In order for something to be able to disproportionate or auto-oxidize, whatever word you want to use, it has to be found on both sides of the table. That's the only way it's going to work. So there's very, very few things that even have the capacity to do this. One of them, for example, is water. Here's water, and here's water. Water is on both sides of the table. It is theoretically possible to take water and cause water to break up backwards this way into oxygen gas and 4 hydrogen ions, but simultaneous have water turn into hydrogen gas and 2 hydroxide ions. Does anybody know how you do that? It's called the electrolysis of water. Yeah, if you add an electrical current to water, which basically, when we talk about these voltage numbers later, if we actually add some voltage, normally water by itself is not a spontaneous reaction. But we can actually force water to basically break up into hydrogen and oxygen. So there's a few other ones on the table. The main ones involve iron, lead, and chromium, just so you're aware of them. Let me see if I can just point them out to you real quick. We've done this one already a couple times today. Here's iron 2+, and here's iron 2+. It's not a spontaneous reaction, but theoretically, iron could react both oxidizing and reducing. Chromium 2+ is found right here and right here, so it also has that possibility. And tin 2+ is right here and right here. It can do that. I should point out, this DAB data table is not comprehensive. There are more reactions than are just listed on this table that you could use. So like another one might be lead 2+. Lead 2+ could go up to 4+, or down to solid lead. That makes sense? So, long story short, because I think I've said this way too more than I need to. If something has the ability to both gain and lose electrons simultaneously, that's what auto-oxidation is. It's usually very easy to pick out these questions on the diploma. They're just going to ask you, here's 4 equations, tell me which one is undergoing disproportionation. And you just have to look for a chemical species that is going from like 2 up to 0, and from 2 down to 0, but from 2 up to 3. All right, cool. Questions, comments, concerns, conundrums, etc. That make sense? Okay, so yeah, like half an hour today. If I can give some advice then for the next today plus tomorrow, print off the lab, start looking at the post-lab questions on the lab. You can probably do that a little bit. Print off the assignment. You can't do all of the assignment, but you can probably start. If anything on the assignment asks you for something called a cell potential, or if it asks you for something like an E with a little 0 up here for a cell, we're going to get to that. Those are the numbers right here. I don't want to bite off I don't want to bite off too much right now, okay? But you can probably do everything else in terms of writing reactions if you skip that section. And then the last thing, you really should try some of the questions on that worksheet I gave you. It's not for marks. I will mark it for you if you want. But you should do it just for the practice, just to get familiar with that table. Sound good? Cool. And break.